introduction and the invitation. So, it's a long time since I was in the audience for the cups in my undergraduate days, so it's nice to be back. So, I'm going to tell you about what we can do with electrons in solids. So we want to play with electrons, but we don't want to do them, just hold them in a vacuum or something, which is quite complicated. We want to make a lab inner chip, you could say. So somewhere where we can hold electrons, and I'm going to demonstrate that we can treat them as waves. They behave as quantum mechanical particles, or as individual particles, individual electrons. We can trap them, and then we can move them around. And I'll try and illustrate why that might be useful, and then what we can do to try to get them to emit single photons of light. So this is always a collaborative effort, so all these people here have contributed a lot to the work. We do experiments, so we have to make samples. That requires working in a clean room, using big pieces of equipment, using good materials. You have growers, you have people who do some lithography, and then lots of students and postdocs who help and work on the thing for a 3-year project and come up with the answer in the end that I then pick up and give talks about. So we get some funding, EPSRC and NPL and the European Union up to now. And so we have quite a useful European Union thing. It's with the Soul Training Network. It's an international training network. So if you're ever thinking about a PhD and you see an advert for an ITN somewhere in Europe, it's quite a good thing to get involved with, because there's a group of different universities within Europe getting together to work on a particular topic. They each have a student or two, and those students are expected to be very independent, but to work together to organise things. You get extra funding and so on. So, and there are meetings together every 6 months or so. So I think my students have benefited from that sort of network. So, can I just ask, because I'm going to talk about quantum mechanics, I would like to assume that most of you know everything about quantum mechanics, but there are probably some first years who only started doing quantum mechanics yesterday. So who's the first year here? Quite a few, so that's fine, because I will not assume a knowledge of quantum mechanics. I'll just introduce little bits of it and what I think we need as we go along. So I've said we're going to try and work in solids. I'm going to demonstrate to you that electrons in solids behave quantum mechanically, but still as single particles if we want them to. And I'll go through a number of results using various geometries. An antidot is a bump in the potential, so electrons go in a ring around them, or 1D channels, so just a single line the electrons have to go through, or dots where we confine electrons in all dimensions, so they're zero-dimensional, and then we see them behaving as single charges. And eventually I'll get to talking about what we can do to take such dots, such quantum dots as we call them, and move them around, so capture an electron, move it around through the material along some channel, and then maybe send it back again. We have to detect it when we start and when we received it, and then send it back and forth, and that's why I call this ping-pong. It's more like a game of catch, really, but still, we send the electron back and forth, and that's quite fun. So everything here I find fun to do. It's interesting to see quantum mechanics in action, it's interesting to hold individual electrons and play with them, and so on. And so once we've done things like ping-pong, we then decided to try and emit single photons. If you can produce single electrons, why not get them to emit, turn into a single photon by recombining with a missing electron, which we call a hole, and so on. So that's where I'll come to. That's our latest results. So you obviously know that electrons are charged particles, and you're familiar with them being in an atom, for example, orbiting around the nucleus, and that was really where quantum mechanics began. People had to understand why electrons don't spiral down into the nucleus, because they should be radiating energy classically. And quantum mechanics said, originally Bohr said, well, they must have quantized orbits, but he had no idea why. Quantum mechanics came along, Schrödinger equation and so on, and explained that better. And I'm not going to go into the details of that. But suffice it to say that we understand now the properties of electrons by thinking about them as a a wave function, some wave that propagates in particular ways, so that's interesting, but if you only see it in an atom, it's very hard to know what's going on. And so one can try to do experiments with free electrons, say a beam of electrons. You might try to do some interference experiment or something. And such beams of electrons are used in electron microscopes, or used to be used in cathode ray tubes. We don't have cathode ray tubes, we've all gone over to LCD these days. But beams of electrons in free space, in a vacuum, were quite popular, and are still very important in microscopes, electron microscopes. But obviously electrons are seen in solids, in wires. It's interesting, if you look in the Cavendish Museum, above the Pippard Lecture Theatre, there's a letter from J.J. Thomson, 10 years after he discovered the electron in vacuum, writing to someone who talked about current flowing through a wire, saying, I think maybe your corpuscles might be my electrons. And so it's very sort of reserved letter, not saying I'm sure of it, but just think about it. So if you decipher what he's written, it's actually quite interesting. But that was in about 1908 or something like that. So we know that electrons move through a wire, but you would never expect really that you've got so many electrons going through the wire, and the wire is just a piece of material, it's not particularly pure, it's not particularly clean or cold or anything. So electrons are going to be disturbed very strongly, and they'll interact with each other and so on. So it's quite hard to imagine that such a wire could show quantum effects as such, and most of the time it doesn't. But then you could say, well, okay, let's make a very pure piece of material, let's cool it down to very low temperatures, so there's very little to scatter the electrons. But then you think, well, actually the electrons are all bound to their individual atoms, so why would they be moving in the first place? Why would you be able to pass current through an object? And so there you need third-year quantum condensed matter course that I'm supervising at the moment to describe that in properly. But it does turn out that you can think about a wave of electron probability going through a crystal, and the electrons manage to sort of escape from their parent ions if it's a conductor. And so you have bands of allowed states where electrons can move through the material, and then you have gaps and so on. And whether a material is an insulator or a conductor depends on where the highest occupied state is, whether it's in the middle of a band or in a gap. So solids are interesting, there's a lot of variety, but we can try to think, we have to think quantum mechanically to understand any of that band structure. But also we can use solids to look at the individual behaviours of individual electrons or waves of electrons and see them behaving, showing quantum mechanics, show it behaving like wave functions, behaving as coherent waves. So yes, we can do all these things, and I'm going to demonstrate that to you with various results. So for the first years, I think you started quantum mechanics on a lecture yesterday or sometime like that, so you don't know a great deal, but you know that particles, there's this thing called wave-particle duality. Sometimes we have to talk about particles, sometimes waves, and so you can't know where a particle is and at what speed it's moving at the same time. So you can know something about its energy or wavelength, and you know something about its position, but you can't know both things. So either you have to think about it as particle and know nothing about its position, its momentum and wavelength, or you know a lot about its energy very precisely, but you have no idea where it is. But more often you choose some sort of wave packet, which is something in between those two. You've got some idea of how localized it is, and some idea about what energy it's got. And so Heisenberg's uncertainty principle allows you to have both those things, but not too much of either of them. And we have a wave function, this psi of x, that, in one dimension, that describes the probability, which is mod psi squared, dx, of finding a particle between x and x plus dx. So that's our probability, that's what the wave function actually means, and I won't say anything more about that, really. But because it behaves as a wave, we then do the things that you've always learnt about that waves can do. They can be reflected, they can interfere, and so on. And as I said, if we want to know where a particle is, we have to confine it in some way. So a confined particle is described by a wave packet. Otherwise, we describe it as something with a single frequency. So, well,
in real solid-state physics, you alternate between those different things. Often you just think about a particle as having a particular wavelength, a particular energy, but you've no idea where it is in the solid. So with this interference, that's what I'm going to show to start off with. You get constructive or destructive interference depending on how the wave bounces back on itself. And again, yes, we can see this in a solid. So in a solid, what do? What can you measure about electrons? But the simplest thing is to pass a current through the solid and see what happens. So this is a typical type of structure that one makes in a solid. It's called a Hall bar. So if you've got a layer of conduction of electrons at the surface, then you just pattern the surface in a particular shape. So it's a long bar, basically a wire, but it's got some terminals on the sides and some contacts at the end. So these orange things are what we call ohmic contacts because they obey Ohm's law, so current flows in and out of the material through that. So I'm going to be talking about semiconductors. They can conduct very well, but they don't have many electrons, which means when we change voltages nearby and so on, we can change the number of electrons easily. Whereas a metal conducts nicely, but it has so many electrons that if you tried to change a voltage near another piece of metal, it would hardly have any impact on that metal. So metals just conduct perfectly all the time. Semiconductors conduct when you want them to. You can change a voltage and turn them off, or turn them on. So that's why the semiconductor industry works, because you have transistors which can be controlled by a third terminal. So we're going to make use of that idea all the time. But here we have a sea of electrons in this region. We call it a 2D electron gas. So you guess that it's a two-dimensional layer of electrons that we've managed to achieve very close to the surface. And in this example, we apply a magnetic field perpendicular to the screen, perpendicular to this Hall bar. The Lorentz force pushes electrons off to the side, let's say to the left. And so electrons coming out of here get pushed to the side of the sample, at least the ones that you've managed to excite by putting a voltage on this end. They go along the edge here, they go into contacts and along the edge and come out into this drain, from source to drain along that top edge. And the ones coming back from the drain along to the source at a slightly lower energy, because we have a lower voltage on this drain than on the source, come back along the bottom edge. So if you think about what resistance is, so resistance is voltage divided by current, V equals IR. So the resistance of this thing depends on how much current manages to flow for a given voltage. And so if all this current that starts out of the top left manages to get to the top right without being scattered so that it comes back, then the resistance will be zero because there's no voltage drop from there to there. And normally you'd be very surprised if that happened because everything you come across has some finite resistance. And semiconductors have a finite resistance, they're not superconductors. But under some circumstances, at certain magnetic fields, we'll see that the voltage drop between this probe and that probe can drop to zero. So we can use these extra voltage probes to measure whether there's any scattering in these what we call edge states along this top surface. And so if you measure the voltage, what we call the Hall voltage in this case here, or the longitudinal voltage here, so that's measured across here is the Hall voltage, or the longitudinal voltage measured along here. So this longitudinal voltage is the one that's going to drop down to zero at certain magnetic fields. So that tells you that these edge states have become extremely well defined at particular magnetic fields, and there's no scattering across the sample here, and so no voltage drop from here to here. So that's the quantum Hall effect. It was discovered in the early 80s, or end of the 70s, and got a Nobel Prize. And the reason it's called the quantum Hall effect is the Hall effect is something you've probably come across even at school. It's a straight line. It's proportional. The voltage across the sample when there's current flowing is proportional to the magnetic field. So it's a straight line. And my supervisor, Mike Pepper, made a sample. He knew the Hall effect would be a straight line, and he sent it to Klaus von Klitzing in Germany, who measured it and saw these plateaus and got the Nobel Prize. So always don't assume things. If you can, just check things, because he didn't realise that there were going to be some plateaus here that no one had ever seen before, and because Clausen and Klitzing bothered to measure them and realised that they were extremely well quantized, he got the Nobel Prize. And now the ohm is calibrated from the height of this plateau. So it's in h over e squared is 25 kiloohms roughly, but the ohm is defined in terms of h over e squared. So fundamental constants. Then another Nobel Prize measure the same sort of two-dimensional system, but improve the quality. And what we saw earlier in the previous slide was down here, and now at higher fields or lower densities, and higher quality material, you start to see a huge array of different oscillations, so lots of zeros and lots of little wiggles that look as if they would like to be zero if they were higher quality, and lots of plateaus in the Hall voltage. So a lot going on, and I'm not going to say anything more about it, but you can see that complicated things are going on. The quantum Hall effect could be described in terms of electrons just moving through as ordinary particles, not interacting with anything else. Fractional quantum Hall effect, as this is called, because all these plateaus, instead of occurring at 1 over 1 or 1 over 2 or 1 over 3 on this of h over e squared here, occurs at some fractional value. So there's clearly a pattern. You see even here, I don't know, 4/3, 5, 7, what is it? Where should we go from here? So 6/13, 5/11, 4/9, 3/7, 2/5. It's particular numbers on the top and bottom of those fractions in a series. So that's all been understood to some extent, but we have to understand that electrons interact with each other. So that's a very interesting area, and it's something that I'm interested in thinking about in 1D systems, but I won't have time to go into it here. So these, in a 2D system or a narrow wire, interactions can be important, but you can hope to see interactions and then never see them, because actually a lot of the time particles, even in a solid, behave as if interactions are unimportant, and that's quite hard to get to grips with sometimes. But at least I'll demonstrate that that is the case today. So here's my Hall bar. It has no scattering. Can we controllably introduce scattering? There we go. So here we put something on the sides of the Hall bar that brings the edge states in towards the middle, and we have a little bump in the potential in the middle, that black dot, which we call an anti-dot, because it's excluding electrons from that region. We have electrons here, but not in that dot in the middle, not outside in these white patches, but everywhere else we have an edge state going on here. Possibility of getting across to an edge state that's going around that loop here. Somewhere I have a picture of that. Don't know where it's gone. Okay, I had a nice diagram of that antidot. So you just have to imagine a potential bump that these states are going around. Other states, as I said, have come along here and along there, and electrons make their way across this small distance here and across there by tunnelling. So this is another quantum mechanical property. Classically, they wouldn't be able to get across, but they can tunnel across. They've got a probability of getting across into these other states. And so what's happening is we've got electrons going round in a loop around that little antidot in the middle. And so that's like a standing wave. They come back on themselves, not by bouncing back and forth as waves on a string, but by going around, like going around an atom, an electron going around an atom. It comes back on itself and superposes with its tail or whatever, and they're just going around together. If they come in phase, then that builds up amplitude. But if they come exactly out of phase, that cancels out. So that's destructive interference, and you don't have an allowed state at that point. So what we see is this, which is quite striking. So this is measuring the resistance of a Hall bar like that. So how much voltage is dropped from there to there. And you can, let's not go into the details about the resistances here, but you can see the resistance is oscillating. Every time we add 1 multiple 2 pi to the loop, so the phase change it increases by 2 pi, we get an oscillation from a peak to a trough and back to a peak. So that's called the Aharonov-Bohm effect, after the theorists who predicted it. And I did my PhD on things like this. It's so fascinating to say, well, quantum mechanics is really coming out in front of you. You see it on a chart recorder, pen, or on the screen as the data is coming out. You see the thing oscillating up and down. You know quantum mechanics that you're taught at undergraduate level really does work. Because this would not exist without quantum mechanics. There's really an interference effect. For every electron that goes round that ring, it interferes with itself. It can't interfere with another electron. And interferes with itself and gives this. And so each electron going round that ring feels the same behaviour. And then you can vary certain parameters, the tunnelling probability across the edges, and get interesting shapes and try and understand different parts of this and look at the line shapes in detail. So that's been an interest of mine in the past. But I'm using it today just to illustrate that quantum mechanics does work in solids. And so where do we go with that? If armed with that information, what might we expect to happen? So, as I say, it takes third year undergraduate level courses to explain the details of why we can think about an electron moving through a crystal without being scattered by all the parent ions that gave rise to the electrons that are moving. But it can be done. So now let's think about, we've got this free electron moving around, but we've tried confining it by making it go round an island, an antidot. But we could put it in a puddle so that instead of being excluded from everywhere on the island, but being able to be everywhere in the sea, we put it in a puddle and it's excluded from all the land that surrounds it. And a central result in quantum mechanics is that when you confine things, you get discrete energy levels. And I've shown you that for my antidot. So if we had a particle in a box, we'd draw a potential like this, so steep walls, and we'd say we've got some energy levels. This would describe waves on a string, on a musical instrument perfectly well. Same idea, same maths. You get a series of energy levels or allowed frequencies. And frequencies and energies are the same thing in quantum mechanics. Give or take a factor of h bar. So they're like standing waves as we saw for the antidot. And then in an atom we have a three-dimensional potential rather than a 1D potential, but the same idea, we get well-defined energy levels and no idea where the electron is in its orbit. We have the idea that each of these energy levels we call a state, so it's a state that doesn't change with time, stationary state as you'll learn to call it, although you can have combinations of those states and make things a little bit more complicated, but then that changes with time. With these states, you can think about we're in a chemistry lab, so they know about, and you've probably done chemistry as well, so you know about the energy levels in atoms and the periodic table and little things like that, so 1s, 2s, 2p, so sets of states in an atom. And you fill every state with 2 electrons, a property called spin, up and down, gives you, and Pauli exclusion principle only allows the pairs of spins in each state. So we have spin degeneracy of factor 2 in each of these states until we get to some level which we start filling in some way. And then we run out of states. So there's always a sort of highest cut-off where we've got electrons filling all the states. Below that, not filling, or no states above, filled states above that at 0 temperature. Notice this diagram has some interactions going on there, but I won't worry about that. So in a crystal we have bands of energy levels, a set of states that you can fill up. I mentioned bands earlier, but I won't go into more detail. So we can think about, here's a band, it's got energy going as a half mv squared, kinetic energy, so it's a parabola in terms of momentum, p squared over 2m, it's the same as a half mv squared. And we fill up all the states up to some maximum, which we call the Fermi energy. So the reason for showing you that is just to say there's a particular energy above which we have empty states and below which we have basically filled states. That's our Fermi energy. And then all the filled states below the Fermi energy can't do very much. They can't be scattered or anything because there's no state to scatter electrons into. Whereas electrons on the Fermi surface can be scattered. And so really everything we talk about is happening at the Fermi surface. And then if you increase the temperature above absolute 0, then by a few kT, well, at the Fermi surface, this range of energies around that are partially occupied is smeared out by something related to kT, the Boltzmann constant, times the temperature. And so if you're doing scattering, which is what gives rise to resistance in a material, so the fact that there is resistance is because electrons are scattered, they can't move perfectly through the material. And that comes from the scattering. So we want to get rid of that, so we work at very low temperatures. So everything I show you will be at low temperatures, liquid helium temperatures below 4 Kelvin. So just to tell you what sort of material we use, we grow very high quality, ultra high quality semiconductor material. So we start with gallium arsenide. So this diagram has been turned on its side so that the horizontal axis here is distance down from the surface of the material down into the material. But we actually grow it from a substrate here, grow layers, atomic layers of gallium arsenic as a crystal here, gallium arsenide, and then in interface with another material, aluminium gallium arsenide. Atomically flat interface, and then put some doping in, so some impurities, and then a bit of gallium arsenide at the top, and that's the surface. And if you look at the energy diagram that gives, so this is the energy of electrons that are free to move in what we call the conduction band in the material, then it looks like this. So this is energy up here, which is why I made it vertical, as a function of position. And so at this interface between the outgas and the gallium arsenide, there's a step up. So outgas has a higher band gap, and so electrons can't, would prefer to be in the gallium arsenide because it's lower energy than in the outgas. And so the trick, which was part of the reason for seeing the fractional quantum Hall effect that got the Nobel Prize, so the Grover who came up with this trick shared the Nobel Prize for the fractional quantum Hall effect, was to put doping, which is impurities that give rise to the electrons that we're going to use in the material, put them in this material, in the outgas, which is high in energy. So the electrons provided with lots of energy where the positive charges that gave rise to those electrons are left behind. And the reason that would not be a good thing for the electrons to stay there is if the electrons move around among those positive charges, they get scattered very easily, and you get high resistance, and the quantum effects that you want to see are not so visible. But what happens is that there's a lower energy place they can get to, so they might get thermally excited over this barrier, and then you cool it down, and now they're stuck here. They sit in this part here. They're trying to get back to the positive charges over here, but they're happily sitting in a potential well here, and so that's a very narrow well. They're pulled up against this edge because there's a positive charge here. But they're not moving among those positive charges. They're some distance away, and that minimises the scattering. So that really was worth the Nobel Prize for that little trick. So there's an electron wave function here. It's a little potential well, a particle in a box type state. The electrons are all in the same state here, but they have lots of kinetic energy, arbitrary kinetic energy, in the plane of the wafer. So it's out of the screen here. So it's become a two-dimensional system. We've confined one dimension by pulling the electrons up against that barrier. So can we confine electrons more than that? Well, because this is very close to the surface, 100 nanometers usually from the surface, we can put metal on the surface. We can put a negative voltage on that surface, on that metal. So these bits of yellow are bits of metal. They're normally gold, which I colour them yellow. We put a negative voltage on. That depletes this blue layer, which is the electron gas, the 2 deck that I showed. And so underneath the yellow bits, we have no electrons. We've got rid of them. But what happens if you make a little gap between two such pieces of metal? This is what my supervisor, Mike Becker, came up with after not getting the Nobel Prize for the quantum Hall effect, was to just leave a gap between two pieces of metal, and therefore the fringing fields from these gates, as we call them, they deplete underneath, and they start depleting sideways, getting rid of the electrons, but you can control how many electrons in the middle are removed. And so you end up with a narrow channel that starts off fairly wide and gets squeezed just by turning a voltage until it's completely narrow, so until there are no electrons left. So just by changing a voltage, we can take a 1D system that starts wide and deplete it out, remove all the electrons and get to no electrons in there. So if you look at the potential on here, I've sketched or calculated a potential. Typically use some sort of leads here, so you've got a lower potential here, lots of electrons, and a confining potential from the sides. So that's these red bits, the electrons are excluded there, but in this sort of turquoise region in the middle, the electrons can get through there easily. And depending on the Fermi energy, so how many electrons you've actually occupied in this thing, so that's the C on both sides. It's the narrow channel that water or electrons can flow through in the middle, and we can squeeze that channel, move it up to control how many electrons get through. So in that narrow channel we have quantum mechanics. We have confinement. The potential looks like this dashed line, it's a parabola to a good approximation, and we get wave functions that look like this, a bit like the particle in a box wave functions. They've got half wavelength, one whole wavelength, and so on, but just slight variations. So that's confinement across the 1D channel, but we still have kinetic energy along the channel. So each electron has one of these wave functions. It's in one of those subbands, as we call it. But each electron can have a different kinetic energy along the channel. So we've still got one dimension that we haven't quantized. So that's why we, instead of calling it a state or a band, it's a subband. It's sort of underneath a band. It's part of a band. It's still got a set of states that are allowed. And it turns out that no theorist had predicted this before it was observed in our lab, that the conductance, which is 1 over the resistance, has steps. Each subband carries the same amount of current per unit voltage. Would you believe that that is real data? So this is measuring the conductance, that's 1 over the resistance, as a function of gate voltage. We're squeezing the gate voltage. So we're squeezing the channel. So by changing the voltage on these yellow things, we're squeezing that blue bit down the middle. That has a set of subbands. So each subband is one of these states. And if you see 20 steps here, it means we've gone up to the 20th of these states up here. So something with 10 wavelengths across the channel is actually still resolvable separately from the 19th and the 18th and so on. So you can count all these, it gets up to about 23. And the height of this, so the conductance, is in units of 2e squared over h. 2 is for spin. E squared over h is, we saw h over e squared in the quantum Hall effect. It's the same idea that resistance is in units of h over e squared, and again it seems quantized. It's not quantized as accurately as in the quantum Hall effect though. So you see these steps. We can change the density by shining a light, and you get a different dependence on gate voltage, but still the steps are in the same places where these dashed lines are. So it really is a robust effect. But it's not particularly quantized. It hasn't become the standard of resistance, whereas the quantum Hall effect did. So yeah, we could apply a magnetic field and actually split these states. So instead of 2e squared over h, you see e squared over h steps, and that means the spin degeneracy has been split. I don't need to go into details of that. So thinking about what we have going on in quantum mechanics, we know about waves. I've shown you examples of where waves, electrons do behave as waves in materials. We can confine them, we can make them do interference experiments, we can see the discrete energy levels as you get in atoms. So another common thing in quantum mechanics is tunneling. So you have a barrier that, so this is energy, or potential, V, and this is position, and so there's a barrier someone's provided, and the electron wave comes along and classically would not be able to get over that barrier. There's not enough energy, so this black line represents the energy of the particle. The red thing is the wave function. So it's coming along quite happily, a large amplitude wave function. It hits the barrier, and most of it's going to be reflected. But classically, all would be reflected. Quantum mechanically, there's an evanescent wave. It's decaying away into the material, because this barrier is not infinitely high and not infinitely thick. So at some point, this wave finds the other side of the barrier and comes out, and then it starts oscillating again because it's allowed to. It's a classically allowed region. So this is what tunneling is. There's a chance that the wave has managed to get through that barrier. So you'll calculate this in quantum mechanics if you haven't done already. and it's tunneling. It's a good name for it. It's trying to get through this barrier. And we can use gates like those squeezing the Y1D channel to control a tunnel barrier and just change its height and change its width and so on. So we can control the amount of tunneling. So this brings me to artificial atoms. I want to make quantum dots, and I better get a move on doing so. So an artificial atom is something that's confined in all 3 dimensions. So we use the background positive potential to attract electrons. That's the donors we put in. We use gates nearby, put negative voltages on them to confine electrons, repel them into the middle, getting rid of the electrons underneath the gates, pushing or just only allowing them in the gap between gates. So here's an example of a device with various gates shown in light grey here. This electron micrograph. This distance here is something less than a micron, millionth of a metre. And so in the middle there is this green dot that represents an electron, or a few electrons that have been trapped in this dot. And maybe it's easier to see in a dot like this, so there's a puddle there, and there are tunnel barriers on either side. I'll say a bit more about those in a minute. But that's where the electrons are confined in the middle, but to notice that they are there, we have to pass a current through the dot. We want to see if current can flow and if its passage is affected by how many electrons are in the dot, or whether there's n plus a half electrons in the dot. So this is what the potential looks like. These barriers we can control by changing those gate voltages on these gates, and so this is the potential energy shown in black here. There's some trapped states in the middle of the dot, so it looks like an atom. It's got discrete energy levels. There's a Fermi energy out here. We've got electrons trying to get through at any energy up to the Fermi energy, and no electrons above that. And same on the other side. So we can try and pass a current through, and if there's a state in the dot that we can tunnel into and then out again, then we see current flow. But if it's not lined up with the Fermi energy, we can either get in and be stuck in there. So this electron here, it was easy to fill it. There's no way it's ever going to get out again because it's below the Fermi energy. So the only time we see current flowing through is when the state can tunnel in to an empty state and then tunnel out to an empty state. So we call this a zero-dimensional system because we've confined it in all dimensions. We call it a quantum dot because these energy levels are discrete. So quantum mechanics gives you discrete energy levels. Quite a lot of what I talk about will actually be applicable to non-quantum systems. So because there's another thing that splits energies, and that's the Coulomb interaction between the charged electron and the environment, the other electrons in the dot and all the electrons around. But if you just look at the measurement of the current or conductance through this type of dot, it's another fascinating result. As you change the gate voltage, you can change the conductance from being on to off. This is real data, it's on a log scale, so it's actually changing by 4 orders of magnitude on this particularly good set of results from a particular experiment somewhere in the world. I'm not going to look up the reference in a moment, but so it's not our data, but you can see very similar things. But it all depends on how well you tune these barriers and so on as to how nice your peaks are here. So there's a particular voltage at which the current conductance is high. And the rest of the time the conductance is low, and then it comes up high again and so on. What's happening is you're changing the number of electrons that fit into the dot. So if it's n plus a half electrons can be in the dot, then if you take out an electron, it becomes n minus a half. And if you think about the energy to charge a capacitor, it's q squared over 2c. And if q is just the half electron, that is how it deviates from the background electrons. You've got n electrons in the dot, n plus a half positive charges nearby. The net charge is half an electron. Take out an electron, it goes from minus half e to plus half e. Square it, because the charging energy of a capacitor is the square of the charge. It goes as the square. It's the same energy. So the energy to charge this system doesn't depend on whether you've got plus a half electron or minus half electron. And at that point, electron can flow in and flow out, and flow in and flow out, and current just flows because you've satisfied this Coulomb charging energy, as it's called. But at any other energy, you've got any other voltage here, you don't have this nice equality between the energy with an electron and the energy without an electron. And so it costs a certain amount of energy to go in or out. Here's a plot of source-drain bias, source-drain voltage that provides that energy as a function of gate voltage. And so all these white patches are where no current flows, and then you see these peaks. So along this middle line, those are the peaks that are shown here. But then as you go out in energy, you can, in some places, you can provide enough energy very quickly to get the electron in and out. But in others, you have to go to a high bias to get the electron in and out. So that shows that we can make quantum dots that have quantum mechanics and this charging energy, this Coulomb charging energy. And if you look at this, you see each of these diamonds, that the size of the diamond tells you the energy level spacing. And it is coming and going. So there's a finite amount, which is the classical charging of capacitor energy, E squared over C. C is the capacitance. But there are these big diamonds and small diamonds. And so 2 and 6 and 12 are large. And if you think about energy levels in an atom, between 1s and 2s is large energy, then between 2s and 3, or 2p and 3s, and so on, they're large energies. But the 2p states are degenerate. There are 6 levels. And I think here it's the 4 because it's 2-dimensional instead of 3-dimensional. So there are 4 levels here. This is like a 1s and a 1p or something. So there's some degeneracy, levels are quite close together, and you get large energy as you go to the next one. So this is quantum mechanical energy levels plus the Coulomb charging. Okay, so I've just illustrated, probably in too much detail, but I've illustrated why we trust that electrons behave in a controllable quantum mechanical single particle way. We can confine individual numbers of electrons, so integer numbers of electrons in a dot. We can make electrons behave as waves, whilst tunneling in and out of that dot, and so on. So it's fun to do. I always like doing experiments like this. It does help you test quantum mechanics and how interactions between electrons can be important in some cases, but actually utterly unimportant in other cases. And the theories that describe those are simple and elegant, if you like. We can talk about quasi-particles instead of particles, so there's a type of particle that's going through. It looks like a particle. It may not be actually an electron, but it behaves like an electron. It has the same charge usually, and so on. So that's what the price you pay in a solid. But the theories are very nice if you can understand them. Once you've done them, they have nice predictions. So what else can we do? Well, you've had a talk on quantum computing, I think last term, so you all know about quantum computing, I guess, but I'm just going to mention it because it's the sort of buzzword these days. It's the thing that people would like to be able to do, and it sounds highly reliant on quantum mechanics. And it's highly reliant on solids most of the time. We want to treat electrons moving through solids as if they are quantum mechanical pieces of information. And normally, at least in semiconductors, when you try to make a quantum computer, you want to use the property called spin of electrons, so it can be up or down. It's got these two values. If you've decided on a direction, maybe of your magnetic field, the spin is either aligned to that when you measure it, or anti-aligned when you measure it. And the property that's most important from spin is that in a magnet, in a ferromagnet, all those spins want to line up. And when they all do line up, then that gives a permanent magnetization, so that gives a magnetic field from a permanent magnet. But I won't go into the details of that. But if you want to think about spin, I've said it can be up or down. That's like being on the north pole or the south pole of a sphere. But quantum mechanically, it can be in a superposition of those two states. So quantum mechanically, you can be in a combination of all of the discrete states that we've talked about up to now. And so with these two states, if it's a two-state system, it's either up or it's down. Those are the stationary states. We could try to manipulate it so it moves around from the North Pole to the equator. So think of this as a sphere, and here's the North Pole, what we call 0, and here's the South Pole, which we call 1. So it looks like a bit of information, a binary digit. It's 0 or 1. But it's a quantum bit or a qubit, because it can actually be represented, or this system can be in any position on this sphere. So we know we have to normalize wave functions, so we can't have a different radius on this sphere. So it has to be on the surface of the sphere. But we add these two with complex numbers, so we can we can go around the equator or to any point in the two-dimensional surface of that sphere. And they're not individual states, but the system can be prepared in any point on that surface. So if you say, my computer I'm going to load a register in my computer with the number 0, that's fine. I can load it with 1. There's no such thing in a classical computer as 0 plus 1, or something like that, or a mixture of 0 and 1. The great thing about it is, if it's somewhere in between, then you know that's noise and it will be rounded down or rounded up, so it's immune to noise. Unfortunately, quantum computers are not immune to noise. So the idea here is that if you can get rid of that noise, you can actually rotate, you can do some operation that rotates the qubit around to the equator, for example, and it rotates it around the equator, rotates it down to the south pole or whatever. And so actually your bit of information is both up and down, both 0 and 1. If you then put lots of these together, you get lots of bits in your register, like a 64-bit processor or whatever, can handle 64-bit numbers. That's 2 to the power of 64 different numbers. If you had 64 qubits, it would be simultaneously in a superposition of 2 to the 64 different states. It would be exploring simultaneously all those different values. So that's an enormous number of values. And so that's very powerful, if only we can make it. So there's a lot of effort going into making it, using another property, which is when you bring 2 qubits together, you get entanglement. You might start with 2 spins that are independent, but if they come close together, they have a chance of swapping, but maybe they didn't swap, so you don't know which process happened, and so they're in a superposition of having swapped and not having swapped. So now these are so-called entangled particles. I won't go into why quantum is bound to be better than classical computation for certain problems. I've got nice pictures of attempts by people to make quantum computers, just to show that there's quite a lot of companies involved now, IBM and Google, and D-Wave was the first company to try to make a product. And that's in superconductors. So superconductors are sort of leading the way with quantum computing at the moment. But semiconductors may come up behind because they may end up being better in some way, more scalable in some way. And so people use sets of gates in semiconductors, like I've been talking about. Lots of gates, look like rather strange things here, but those are all gates defining a very narrow channel here. People can implant a single atom just below the surface. So people in Australia, University of New South Wales, implant individual atoms. And then they can have the spin on that atom. It's very isolated from everything else unless they want it to be connected. And then their difficulty is actually getting it connected to another qubit to do any operations. And you need to do all this at extremely low temperatures, like 10 millikelvin. You need a dilution fridge, which is something that can get down to that low temperature. It costs £30 million or whatever you want to spend on it. And this picture is impressive because we used to have just a few wires going down into such cryostats. Now the companies will, if you pay them enough, will put 100 coax cables going down into the cryostat, each of them with little loops in and filtering and thermal anchoring and so on. So it's a big task to get enough wires into your system to actually do some interesting measurements. So let me move on rapidly to why what I do might one day be useful for quantum computing. I mean, showing you lots of our old results, but we're trying to play with electrons, and there's a chance that if you've got all these qubits and you can see here's a set of qubits, but you've got to somehow move the information between adjacent qubits in order to entangle them. So in the semiconductor, it's quite hard actually to bring 2 electrons together and then move them apart and so on. You probably need some distance between them in order to get some classical logic gates to play as well. So it might be quite useful to be able to move electrons over some distance. So we use what's called a surface acoustic wave. You can guess what that is. It moves along the surface. It's a sound wave. So it's a lattice distortion. So that's a picture of a lattice. And we set it up with some fingers on a surface on a piezoelectric material. So piezoelectric material is one where you apply a voltage and it stretches or changes its size. So by applying gallium arsenide, my favourite material happens to be piezoelectric. So if we put an array of fingers like this, so entity-shaped fingers, apply voltage between them at 3 gigahertz, we set up an oscillation in the strain travelling along the surface at 3 gigahertz. And along with that strain, there's a potential modulation. And so here we have a 1D channel, like the ones I've shown in the past. So here was the 1D channel we had in the past. If we pinch it off, so it's like that, it has no electrons in it. But we have a sea of electrons at each side, and so if we take a cross-section through that, here is a cross-section potential through it. And the surface acoustic wave, the SAW, can take electrons from this sea of electrons here up to the Fermi energy, and picks electrons out of here, so that it collects them, squeezes them into quantum dots. This barrier coming from the surface acoustic wave is pushing electrons together into a narrow dot. Some of them tunnel out because they can't survive in that dot, the dot's not big enough. Others manage to get through, the dot gets a bit deeper because the potential is flattened off. So where the potential is steepest is the critical point for the electrons. They've either survived that till then or they've been pushed out. And once we've got that, we can drag electrons through this thing. And this is a quantum dot. It has the Coulomb-Bouquet idea and so on. So if you try to put a second electron in, there's an energy cost for doing that. And so you either have one electron going through or you have two. But it's quite easy to get it so that it's not 1.5, not sometimes one and sometimes two. And how do I know that? Well, we can get results like this. So this is the current that's pumped through that system. So we don't apply a voltage, we just let the surface acoustic wave drag electrons through. We measure the current. So we call that the acousto-electric current. We plot it in units of E times F. E is the charge, F is the frequency, which is about 3 gigahertz. And so then we change our favourite thing, the gate voltage, that's squeezing the channel. When the channel is very wide open, you get a lot of current pumped through. When it's narrow, you get no current pumped through. And as you open the channel, you get E times F of current, or 2EF, or 3EF. And that EF means that you've got one electron per cycle. So as my diagram, my animation showed, we're pumping one electron through per cycle. And the next step shows 2 electrons going through per cycle, and so on. And you can try to see how flat the plateau is, and you zoom in on it, and the best we can do is about 1 in 2,000 or 1 in 10,000, which isn't good enough to make a current standard. So people in our group have come up with another design for a pump, slightly related to this, but not using surface acoustic wave, but still using gates. And that pumps electrons in an accuracy of about 1 part in a million. A German group that's copying the same design has got about 1 part in 10 million. So it's nearly a current standard, and it's probably going to be, or something like that, will one day soon be a current standard. So the SI units have just been redefined, and current will be defined as the amount of current pumped per second. And once people have actually made devices that you can trust, then they will be used to calibrate current in that way. So we gave up hope that we'd ever get flat enough plateaus to make a current standard and started looking for other things. So what can we do with such dynamic quantum dots where we're pulling electrons through? So we could pump them uphill into a region where we have some missing electrons, what are called holes, and those electrons could recombine with those holes and give out light. So I'll show a little bit of the results on that. Or we could do some things related to quantum computing and then try and read out the spin by generating polarized photons. So photons, light has polarization, so vertical, horizontal polarization, circular polarizations. Electrons have spin, and the two both have angular momentum. So when electrons give out photons, they conserve angular momentum. So you can transfer the information from electrons to photons. So there's a qubits and ones that Chris and Barnes in our group came up with a whole quantum computer based on SORs, and so taking qubits along a channel and doing quantum computations. We've done some experiments linked to dragging electrons along channels. This dark line along here is a channel. The electrons are dragged along there. Everything around there, these light-coloured things, are gates. We've got 18 gates around here. They're all separated with little gaps here, so you can put different voltages on different parts without really disturbing the channel geometry. We've got a tunnel barrier here. The zoom-in shows here a barrier. And so electrons can come along here, have a chance of tunneling across to there and going out there, right there. And you can try to see the quantum mechanical effects of that, which has proved quite difficult. And this was a device with even more gates. It looks pretty, but it's just too complicated to ever work, unfortunately. So then we turned our attention to a slightly simpler device where we can actually capture an electron statically, so it's not moving in the surface acoustic wave, but we can make sure it's just one electron. And then we can try and use the surface acoustic wave to move it. So this might be useful for transferring quantum information for qubits that I've talked about. And so here's a quantum dot. It's a static dot. It's got lots of gates around it. That little circle just tells us where the dot is, where the electron will be confined. And that's the left quantum dot, and that's the right quantum dot. This channel shown by the yellow line is empty. It's squeezed, so it has no electrons in it. And in fact, to prove it has no electrons, or make sure it has no electrons, we send a surface acoustic wave pulse along and sweep out any stragglers, any electrons that got stuck in there. So that's a sketch of the layout, and here's the potential looking along that channel. So here's a little dot. That's where electron can collect, one electron. This is a lead where we can get that electron from. Here's an empty channel. We can try and pump it along there, and another channel, another dot at the end, where we capture the electron. And the way we pick up the electron is to dip one of the gates, so the potential comes down like this. It goes below the Fermi energy of the lead, and that picks up an electron, and we bring the barrier up. So we've scooped up an electron, got that one electron, any spares tunnel out quickly enough, and then we bring the barrier up high, and we capture our electron. Sometimes we deliberately fumble that catch or whatever, and make sure we've done the same operations, but in the wrong order, so we don't capture an electron. So we can compare the case with the same voltages, but where we have no electron in the dot, or where we do have an electron in the dot. And so this is something I haven't mentioned yet, but we can detect the charge on the dot by using a 1D channel. So here is another channel, which is the 1D channel like I showed earlier. So it's squeezed, so it's very highly resistive, it's high resistance, it's very sensitive to any change in gate voltage nearby. But a gate voltage is just where you put electrons onto a piece of metal. If we put an electron into this dot here, that's also like a gate voltage. So one electron on this dot can change the resistance of that constriction there. And so we can actually detect the presence of an electron in this dot. So it was Charles Smith in the Semiconductor Physics Group who came up with that idea of using one channel as a detector of a dot in 1993. And that's now very widely used in trying to make semiconductor qubits. So this blue line is this calibration for changing one of the voltages, so the size of the dot. So we calibrate by not picking up an electron, or we do pick up an electron. When we pick up an electron, we get this red trace. When we don't pick up an electron, we get this. Actually, all the blue and red traces, there are lots of very short traces, and like this, lasts a fraction of a second. You take data of a second, you can see it's stable at that value, or sometimes it jumps. But what you can see in the red traces are, they either take that value, or that value, or that value, or that value, and so on, as you change the size of the dot, or how well you capture the electron. And so this value is quantized, it just corresponds to one electron being in the dot. And this is 2 electrons in the dot, or 3 or 4. So we know exactly how many electrons we have, and we know when we have no electrons. So that's calibrated to say this dot can be held with a finite number of electrons in the dot, a well-known number of electrons in the dot, for as long as we want it to be. You can hold it there for seconds or minutes or hours, probably, if we were patient enough. So there we have the ability, sorry, it's catching up with me now, to pick up electrons and keep them in the dot. So then we send the surface acoustic wave along, maybe from the right here, you can see an animation of what we think we're doing. Here's the electron, that blue dot. The surface acoustic wave has come along, wiggled the potential, pulled down the barrier here, and dragged the electron along here, and it's then been caught by this high barrier at the end and transferred to the other side. So that's what we're trying to do with a surface acoustic wave pulse. It's a very short pulse, 100 nanoseconds, for example. We can fire that along and look to see if we've managed to achieve it. So we detect either the left quantum dot detector or the right quantum dot detector. These are 2 charge detectors like I showed just now. And so we can start with electron 1 means electron is in the dot. So we start that, we send a pulse which is at the time of this blue line. So this is time before pulse arrives, and this is time after. The detector is not a very high bandwidth thing. You can't detect very quickly whether there's an electron in there. So we can't detect the saw pulse going through, but we can detect the result. And here we can say the electron was there, and now it's not there. question is, did it arrive at the other end? And here's an example where it changed from an empty dot at the left to a filled dot at the left. And then there's the case, just for honesty, that where it didn't happen, the electron got stuck somewhere in the middle, came out on the next pulse probably. And here are some other examples where it did come out. So there we are actually sending the electron in the same direction each time. We have to prepare the system anew each time by loading the right dot with the electron and sending it. But to justify this term ping-pong, or cache, whatever, we want to send the electron back. So we have a pulse coming from the right, it sends the electron off to the left. Another pulse then comes in from the left, sends the electron off to the right. And each time we measure things. So here's the left dot, here's the right dot, the detector measurement of each of them. We start, here there's an electron in the dot, it's depopulated, so it goes up to here. And then this one is populated, then it's depopulated, populated, and so on. So we're just sending this same electron back and forth many times. And then, in this case, we deliberately let it get out after the sequence. So you can try to see how many times you can do that. And I think we managed about 60 times. That means that single electron had travelled all of a quarter of a millimetre. So that sounds like a lot on the scale that we're dealing with. And at that point it was joined by another one, so somehow another electron had been pumped in by the sword. So in principle you could imagine doing that perfectly if you designed the device right. So that is the sort of headline result. We can play ping-pong, we can move electrons around, just treat these single electrons. What we'd really like to do is to demonstrate that we can transport spins. There's a competing group, although we're now in this training network, so they're not competing with us anymore, we collaborate with them. They did almost exactly the same thing. We think they saw our paper, our early talk at some point, so they chose exactly the same dimensions for their device. But they did much the same thing, but their transducer, the thing that could send us all from the left-hand end, didn't work. They only had one working, so they couldn't send their electron back. So we had one up on them for that. But they have now managed to demonstrate spin transport, so they can get a reasonably good probability of transporting the same spin along the channel. So they prepare the spin in a quantum dot at one end, which is quite sophisticated, then measure the spin at the other end. And so I wanted to do that, but I had a different way of doing it. It's taken me 4 PhD students to get there. But we have now got there, sort of, but not quite there. But we've got interest in generating photons from these single electrons. So that's the direction we went instead. So, briefly, I'm sure I'm close to the end of my hour, but I think I started about an hour ago. So if you'll let me have a couple more minutes, then I will to show you what we've been trying to do. For 5 minutes maybe. So, we have this device. Let's look at it. What we've got here is I think if we look at the small diagram to start off with, we've got a conduction band and a valence band. I told you about bands and a gap between them. Electrons live in the conduction band. The valence band should be filled, but we can arrange it so we have some gaps in the valence band. We call those holes. So we have a sea of holes on the right-hand side. That took 2 PhD students to get that. And a sea of electrons on the left. Then it takes 2 PhD students to get them together and then get the light out. So one of my students, Sukan Xiao, did this rather nice animation to try to explain what's going on. We have the conduction band, we have a whole lot of electrons ready to be pumped up a slope between the conduction band on the left and the conduction band on the right. The Fermi energy is meant to be about the same in the two sides, but one is in among the holes, one is among the electrons. So there's a slope the electrons have to get up. So this surface acoustic wave, this is the material itself, the gates, and the strain wave coming along, that's the potential wave as well, grabs electrons, takes them up this hill. When they get to being in the conduction band above a sea of holes, they think, well, there's a hole down there, I'd love to fall into that hole. And they just fall in, with some probability. But when they fall in, they've got energy to give away. And that energy corresponds to what comes out as a photon. So the little yellow thing you see going off to the side, if you wanted to continue to play that, is a photon. Oh, we can do better than that. So the photon is coming out, and this animation shows that process repeated. So we're doing this 3 billion times a second. We're sending one electron over. We hope that we've quantized the current as we did before. It's not perfect at the moment, but that's something to optimize. But we're at about one electron going through per cycle. Sometimes it's no electron, so we've tried to sit at the current level that is low enough that we think the probability of having 2 electrons going through is very small. So here comes an electron, it's going to recombine at that point and give out a photon. So recombining is going back into a hole. It's just that's where the electron can be thought of as having come from in the past. So that's our process of emitting lots of photons. And so it's a complicated device structure to make all that. As I said, it took lots of effort to get there. We have complicated gate structures. These black regions are the gates, some side gates, and gates to induce electrons, to induce holes, to try and stop the electrons whizzing past the holes and so on. So we came up with random or complicated patterns, sort of mazes for the electrons to stop them getting out. And etched regions, these purple bits, to make sure the electrons don't get off to the side. So it's been pretty hard to keep the electrons where we wanted them to be. And then you say, okay, we are managing to get electrons across the holes. Can we get light out? So you measure the current through the device without surface acoustic wave, just apply a bias to things like lighting up an LED. This is pretty much an LED. It's a PN junction, if you know about the PN junctions, which is how an LED is made. We've made an LED. Big stuff. And so we apply a voltage, electrons go across, are pulled up that slope, or the slope is pulled down so it's flat, so electrons can get across. So there's current going through. Do we get light? And here's the spectrometer showing that at a particular wavelength, which corresponds to the right energy for those electrons, the band gap of the material, then we get emission that increases as we increase the current and the voltage across the thing. So that's fine. That's with a large source drain bias. But if we then reduce the source drain bias down somewhere over here where there's no current going through, can we get current then? But the only way we can do that is to use the surface acoustic wave to drag the electrons through. And so now as we change the frequency of the surface acoustic wave, there's one resonant frequency, which are fingers that generate the surface acoustic wave are on resonance. So they have a particular frequency. We chose it to be about 1 gigahertz this time. It gives a wavelength of about 3 microns of the acoustic wave. And that has that resonance and the complicated sort of sync function structure that we get with surface acoustic waves. And so the blue curve is the source drain current, the brown curve is the electroluminescence, so that's the light output from the device. So you can see the two go together. So when the surface acoustic wave is pushing electrons through, it's getting light to come out. And we can check the frequency, we can check the spatial resolution. So this is the bottom of a cryostat. It's very hard to look down there for the light, so we had to build a lens assembly, which is a couple of lenses about 2 millimeters in diameter, and they're at the bottom of the cryostat on the end of a stack of piezoelectric positioners, so we can move in X and Y and Z, but we have visibility 1 square micron at the bottom of the chip. So each pixel here is 1 micron by 1 micron. And that then goes into optic fibre and comes out to the room temperature light detector. It goes along the corridor to the spectrometer. So we can laboriously produce an image of what's going on in position, but if we position ourselves in the place where we expect light to come out, or we find light to come out, then we get the best. We then don't have to move too much. So I won't go into much detail, but we can time resolve the light emission now. We have sensitive, very high resolution detectors. They can detect within 20 or 40 picoseconds of a photon coming in. They can detect 1 photon, so they're called avalanche photodiodes. And we can trigger that, so we can trigger the surface acoustic wave pulse and then see that sometimes light comes out immediately. But we know that actually we generated the surface acoustic wave a millimetre away from where it's meant to be used. Sound takes time to travel, it goes at 3 kilometres a second. So actually the sound takes this much time, a nanosecond, so a microsecond, I think 1,000 nanoseconds here, to travel. So this part was some sort of crosstalk. It was just generated by the huge EM wave, the electromagnetic wave that we put in. It caused some light to come out. But then the main thing happened here, which is a lot of oscillation, so a lot of peaks, which I'll show you in a minute, of light emission at every SAW minimum. And we can adjust the settings until there's no crosstalk, so we can say, oh yes, we've got rid of that crosstalk, we just have this. And we can look in detail at the line shapes, and we can say, okay, there's a set of peaks, they're correlated exactly with the SAW frequency, so we know as an electron comes across, it recombines very quickly, then another electron comes across, recombines. We can fit the line shapes and so on, and we can try to see whether we're getting we're really getting one photon per second. And this dip, I can see people are thinking I've gone on too long, so I better stop. So this dip tells us that really we do have nearly, or most of the time, quite a lot of the time, one photon coming out per cycle. There's still plenty of scope for doing more on that, but we are getting there. We can look at line shapes, we can resolve the positions of the emission and say, well, actually, you can see it moving in space and time along a particular line that corresponds to the velocity of the SAW, the sound wave. So in conclusion, electrons in solids do behave like quantum mechanical waves. We can confine electrons, we can confine them as single electrons, we can move those single electrons around along empty channels, we can capture them, play ping-pong with them, and we can get out single photons. And that might make a single photon source that might be useful for transferring quantum information, or in quantum cryptography, where it's important to have single photons that you can be sure when you've set it up in a particular way, no one has intercepted it because they would have disturbed the photon, because the act of measurement disturbs the system. So there, I better stop. So thanks for your attention.